Does fine-tuning LLMs on new knowledge encourage hallucinations? Zorik Gekman, Galyona Roe Aharoni, Matan Eyal Amir Feder, Roy Reichart, Jonathan Herzig Abstract. When large language models are aligned via supervised fine-tuning, they may encounter new factual information that was not acquired through pre-training. It is often conjectured that this can teach the model the behavior of hallucinating factually incorrect responses, as the model is trained to generate facts that are not grounded in its pre-existing knowledge. In this work, we study the impact of such exposure to new knowledge on the capability of the fine-tuned model to utilize its pre-existing knowledge. To this end, we design a controlled setup focused on closed-book QA, where we vary the proportion of the fine-tuning examples that introduce new knowledge. We demonstrate that large language models struggle to acquire new factual knowledge through fine-tuning, as fine-tuning examples that introduce new knowledge are learned significantly slower than those consistent with the model's knowledge. However, we also find that as the examples with new knowledge are eventually learned, they linearly increase the model's tendency to hallucinate. Taken together, our results highlight the risk in introducing new factual knowledge through fine-tuning and support the view that large language models mostly acquire factual knowledge through pre-training, whereas fine-tuning teaches them to use it more efficiently. One introduction. Pre-training large language models, LLMs, on textual corpora embeds substantial factual knowledge in their parameters, which is essential for excelling in various downstream applications. These models often require further alignment to desired behaviors, typically achieved through supervised fine-tuning on instruction-following tasks and preference learning from human feedback. In the fine-tuning phase, the model is usually trained on outputs created by human annotators or other LLMs. As a result, the model may encounter new factual information, extending beyond the knowledge it acquired during pre-training. This raises the question of how LLMs integrate new facts outside of their pre-existing knowledge. One possibility is that the model simply adapts by learning this new factual information. However, a common conjecture posits that such exposure to new knowledge may encourage the model to hallucinate factually incorrect responses, as the model is essentially trained to generate facts that are not grounded in its pre-existing knowledge. Figure 1. Train and development accuracies as a function of the fine-tuning duration when fine-tuning on 50% known and 50% unknown examples. Unknown examples are fitted substantially slower than known. The best development performance is obtained when the LLM fits the majority of the known training examples but only few of the unknown ones. From this point, fitting unknown examples reduces the performance. In this work, we study how learning new factual knowledge through fine-tuning impacts the model's tendency to hallucinate WRT, its pre-existing knowledge, exploring the above conjecture. Point 1. To study the impact of new knowledge, we must be able to assess whether a single fine-tuning example is consistent with the model's knowledge. We propose SLIC, a hierarchy of 4 knowledge categories, derived from a continuous measure that quantifies the agreement between model-generated answers and the ground truth labels. In SLIC, examples are first categorized into known and unknown types, where the latter corresponds to examples with facts that are most likely unknown to the model. The known examples are subsequently split into 3 categories: highly known, maybe known, and weakly known. Figure 2. Equipped with the above method, we carefully design a controlled study focused on closed-book question answering, QA, where we vary the proportion of the fine-tuning examples categorized as unknown while controlling for other factors. Our study empirically demonstrates that learning from unknown fine-tuning examples is linearly correlated with the model's tendency to hallucinate WRT, its pre-existing knowledge. Paragraph 4. Conversely, learning from known examples is correlated with better utilization of pre-existing knowledge. Through an analysis of the training dynamics, we discover that the LLM fits unknown fine-tuning examples substantially slower than known examples. Top plot in Figure 1. This indicates that during fine-tuning, LLMs struggle to integrate new factual knowledge present in the unknown fine-tuning examples. Instead, they mostly learn to expose their pre-existing knowledge using the known fine-tuning examples. From a practical perspective, mitigating overfitting using early stopping, vertical dotted line in Figure 1, can minimize the risk of the hallucinations caused by fitting the unknown examples, since they primarily emerge in later training stages as a form of overfitting, as illustrated by the development performance decline in the bottom plot of Figure 1. Alternatively, we also show that filtering out the unknown fine-tuning examples substantially reduces the risk of overfitting without sacrificing performance. We further evaluate the impact of fine-tuning examples from each of our 3 known knowledge categories on performance. Unexpectedly, we find that a model fine-tuned only on examples from the highest knowledge degree, denoted highly known, does not yield the best results. Our analysis reveals that incorporating maybe-known fine-tuning examples representing facts with lower degrees of certainty plays an important part in properly handling such examples in test time. This indicates that the composition of fine-tuning examples significantly influences the extent to which LLMs effectively utilize their pre-existing knowledge. To summarize, we study the effect of new factual knowledge in the fine-tuning data by designing a controlled setup that isolates this factor. We find that fine-tuning examples that introduce new knowledge are learned slowly, which suggests that LLMs struggle to integrate new knowledge through fine-tuning and supports the view that LLMs mostly acquire knowledge through pre-training. However, we also find that as the model eventually learns new knowledge through fine-tuning, it becomes more prone to hallucinations, its pre-existing knowledge. Collectively, our findings highlight the potential for unintended consequences when introducing new knowledge through fine-tuning, and imply that fine-tuning may be more useful as a mechanism to enhance the utilization of pre-existing knowledge. 2 Study setup. Given a fine-tuning dataset D and a pre-trained LLM M, we denote by MD a model obtained by fine-tuning M on D. To study how new knowledge in D affects MD's performance, we design a controlled setup, creating variants of D with varying proportions of examples that are unknown to. When constructing D, our objective is to reflect instruction tuning on diverse knowledge-intensive tasks while maintaining control over the experimental setting. We thus focus on factual knowledge that can be structured as subject, relation, object triplets, which are converted into closed-book QA format. In this setup, D equals QI AI, N equals 1, where Q is a knowledge-seeking question corresponding to a specific triplet, e.g., where is Paris located? And A is the ground truth answer, e.g., France. To this end, we use entity questions, where triplets from a diverse set of relations from Wikidata are converted to QA pairs. These relations encompass a broad spectrum of factual knowledge. Figure 2. Formal definitions of the SLIC knowledge categories, based on the p-correct measure as defined in Shastak 3a, accompanied with real examples from the annotated entity questions dataset used in our study, including biographical information, geographical data, ownership and authorship details, history, and more. We use the original development and test splits, and we subsample the train split to create different variants of D. We focus on 12 diverse relations and reserve 7 additional relations for an out-of-distribution test set, used only in 4.5. As M, we use the Palm 2M base model. We focus on exact match EM as our evaluation metric 2. Full technical details are in Shastak 3. Quantifying knowledge in LLMs. To assess the effect of new knowledge in D on the performance of MD, we have to annotate each QA pair in D.RT, whether M knows that the answer to Q is A. To estimate this, we define a continuous p-correct measure based on samples from M, and use it to divide QA pairs into 4 knowledge categories. We name this approach SLIC, Sampling-Based Categorization of Knowledge, defining p-correct. We adopt the perspective that M knows that the answer to Q is A if it generates A when prompted to answer Q. Since M is a base model that has not been specifically fine-tuned to follow instructions, we prompt M using in-context learning with few-shot exemplars. Following Rubin et al. 2022, we make sure that the few-shot exemplars have high semantic similarity to Q3. In practice, M can predict different answers since 1. The choice of exemplars influences individual predictions, and 2. Temperature sampling, if used, introduces randomness. To reflect this, we define p-correct QA, MT, as an estimate of how likely is M to accurately generate the correct answer A to Q, when prompted with random few-shot exemplars and using decoding temperature T. For the purposes of our study, we approximate the value of p-correct using nex equals 10 different random 4-shot prompts. For each 4-shot prompt, we predict the greedy answer using t equals 0 and 16 sampled answers using t equals 0.5. P-correct Q A M T equals 0 is estimated by the fraction of correct greedy answers, and p-correct Q A M T 0 by the fraction of correct sampled answers. Full details are in Factsheet C. Deriving knowledge categories from p-correct. We define the unknown category, bottom row in figures 2a and 2b, to represent QA, pairs for which M never predicts the correct answer to Q. In our notations, this means that p-correct QA MT greater than or equal to 0 equals 0. Alternatively, if p-correct QA M T greater than or equal to 0, deity 0, i.e. M sometimes predicts the correct answer to Q, we consider QA as known. In this choice, we posit that if prompting M to answer Q can sometimes result with the correct answer A, then M must have some association with the relevant fact. Recognizing that knowledge can vary in degrees of certainty and extent, we divide the known QA pairs into 3 distinct categories, top 3 rows in tables 2a and 2b. Motivated by the principle that M should consistently predict A if QA is known, we put emphasis on greedy decoding outcomes, represented with p-correct QA M T equal to 0. Figure 3. Test performance as a function of the percent of unknown examples in the fine-tuning dataset D. In A, each line corresponds to a different fixed number of epochs, except the early stop, which corresponds to early stopping using the development set, see factor 4. In B, we present the ablation from factor 4.2. Full lines correspond to fine-tuning on D and are identical to A. Dotted lines correspond to fine-tuning on the ablated variance dk known, where unknown examples are filtered out. For 0% unknown D equals D known, and for 100% unknown, there is no dk known. Highly known represents QA, pairs for which M always greedily predicts A. If M sometimes but not always greedily predicts A, we consider QA as maybe known. Lastly, if M never greedily predicts A, we classify QA as weakly known. We apply SLIC to annotate each QA pair in our dataset with its knowledge category WRT. M5, we analyze the quality of our categories in BARC 6. 4. How harmful are unknown examples? In this section, we study the effect of new knowledge in the fine-tuning dataset D on performance. To isolate this effect, we vary the proportion of unknown examples in D while controlling for other factors. Specifically, we fix D and create variants of D with X% of unknown and 100 minus X% known examples. Full details in Part E. We treat the known categories collectively, see Figure 2a, and provide a per-category analysis in Circa 5. We denote early stopping based on the development set as early stop, happens after 5 to 10 epochs, and 50 fine-tuning epochs as convergence, as at this point M always completely fits D, i.e. 100% training accuracy. We measure test performance as a proxy for hallucinations since we are in a closed-book QA setup with disjoint-trained test splits, where the model has to use its pre-existing knowledge to answer test questions. See Paragraph B for further discussion. 4.1 Higher unknown ratio is proportional to performance degradation. Figure 3a presents the performance as a function of the percent of unknown examples in D for different fine-tuning durations. Higher % unknown leads to performance degradation, regardless of the fine-tuning duration, which indicates that unknown examples are less useful than known. Performance is also strongly affected by the fine-tuning duration, with early stop typically yielding the best performance. Training for more epochs usually reduces performance, with the lowest performance observed for convergence, which can be attributed to overfitting D. Interestingly, this effect increases with larger % unknown. The interline spacing from early stop exhibits a monotonic increase along the positive x-axis, suggesting that a higher % unknown increases the risk of overfitting. 4.2 Unknown examples. Harmful or neutral? Since D is fixed, performance drops for higher % unknown could stem from simply the lower number of the known fine-tuning examples. Thus, it is still not clear if unknown examples are harmful or neutral. To address this, we measure the effect of filtering out all the unknown examples from D. For each D variant, we create a corresponding ablated variant D known, consisting only from the known examples in D, If D has 25% unknown, we filter them out and are left with the remaining 75% known examples and get D known B equal to 0.75 times D. Figure 3b presents the results. Perhaps surprisingly for early stop, the results for D are almost top. Figure 4, the state of the examples in the fine-tuning dataset D after early stop. For each variant of D y-axis, we illustrate which portion of the examples in D the model fits, i.e. predicts the correct answer for Q, identical to DK known, indicating that the unknown examples had a neutral effect on performance, as their removal had minimal impact. Conversely, the convergence results show that with longer training, unknown examples are actually very harmful. In this case, D underperforms DK known, and the gap between them is proportional to the unknown ratio. Interestingly, for DK known, the gap between early stop and convergence is very small, dotted lines, while this gap is very large for D, full lines. This indicates that the presence of unknown examples is what makes the variants with higher unknown ratios more prone to overfitting. 4.3 unknown examples are fitted slower than known examples. We showed that unknown examples are harmful, but their negative effect is mostly materialized in later training stages and thus can be empirically avoided using early stopping. To better understand these trends, we analyzed the training dynamics by examining which fine-tuning examples in D were fitted by M during various fine-tuning stages. Figure 1 presents the train accuracy of the known and unknown subsets of D as a function of the fine-tuning duration. The development accuracy is presented in a zoomed-in plot at the bottom, as it falls within a narrower range. We include a breakdown of the train accuracy per known category in F. M fits unknown fine-tuning examples substantially slower than known. In early stop, vertical dotted line, M reaches peak performance on the development set, while fitting the majority of the known examples but only a small fraction of the unknown. In Figure 4, we show that this behavior is consistent across all our variants of D. This can explain why in early stop the unknown examples had a neutral effect on performance, 4.2. Table 1. Results of our linear model for predicting the test accuracy as defined by equation 1, as at this point M still did not fit most of them. Lastly, since unknown examples are the ones that are likely to introduce new factual knowledge, their significantly slow fitting rate suggests that LLMs struggle to acquire new factual knowledge through fine-tuning. Instead, they learn to expose their pre-existing knowledge using the known examples. 4.4. The influence of unknown versus known on accuracy. A linear model perspective. Figure 1 demonstrates that after the development performance peaks at early stop, vertical dotted line, it deteriorates as M gradually fits more Fuessian unknown examples. In this section, we aim to characterize this relationship more accurately by assessing whether a simple linear dependency can tie the impact of fitting of error, known and unknown training examples on test accuracy. To this end, we use the following linear regression model. See equation, where NKN and UNK are the number of the known and unknown examples in D that M fits. We estimate the coefficient 6 by collecting accuracy NKN, NUNK values after each epoch from models fine-tuned on all D variants. Table 1 presents the results, top row. The high R2 indicates a strong linear relationship between test accuracy and the type of training examples that are fitted. Our model entails that fitting unknown examples hurts performance, bait UNK 0, while fitting known examples improves it, bait KN 0. The estimated negative impact from unknown roughly matches the positive impact from known, approximately equal to bait KN. 4.5. Generalization to new relations. In the above setup, the QA pairs in the test set correspond to triplets with the same set of 12 relations appearing in D. We now investigate whether our observed dynamics has a broader effect on the model's knowledge and transfers to relations not. Table 2. Accuracies for the single category variance from Sacrative 5 across per category subsets of the test set. Full is the original test set, all the categories together. HKN equals highly known equals maybe known, UNK equals unknown. In each column, the best result is in bold, as well as the results for which the difference from the best is not statistically significant with p.05. Significance test details are in TAC I. Represented in D. To test this, we reserve a subset of the relations for an out-of-distribution OOD test set, excluding them from the train and development splits. See SAGACH A for details and tables 4 and 5 for in-distribution versus OOD relations. Our results on the OOD test set reveal similar key insights. 1. Higher unknown ratio leads to lower OOD test performance, and 2. Unknown examples are harmful for OOD performance, but mostly when M fits them. A linear model of the OOD test accuracy, equation 1, shows similar trends. VUNC 0, BKN 0, approximately equal to BKN, and R2 equals 0.95, see Table 1. More details are in Prac H. Overall, our insights transfer across relations. This essentially shows that fine-tuning on unknown examples such as where is E1 located can encourage hallucinations on seemingly unrelated questions, such as who founded E2. This further supports the conclusion that the observed effects likely stem from the model learning the behavior of generating answers that are not grounded in its pre-existing knowledge. 5. Understanding knowledge types, their value and impact. When addressing our main research question on the effect of unknown fine-tuning examples, we treated the known categories collectively for simplicity, see Figure 2a. We now examine the effect of each category, exploring the following questions. Q1. How training examples from each category impact the test performance. Q2. What is the model's performance across test examples from each category? To address Q1, we created single-category variants of the fine-tuning dataset D. A variant of D consisting solely of examples from the category CAT is denoted as DCAT. For reference, we include a variant with the natural categories distribution in entity questions, denoted DNatural. D is fixed and identical to our experiments in Sharika 4. To address Q2, we further break down the test set performance by category. Table 2 presents the results. Maybe-known examples are essential. Since unknown examples are harmful, one might expect that it would be best to fine-tune on the most exemplary highly known examples. Surprisingly, D highly known does not obtain the best overall results, as it excels on highly known test examples, yet its performance on the remaining categories is inferior. D may be known yields the best overall performance. Compared to D highly known, D may be known enhances MD's performance on may be known 60.1 to 69.9 without compromising performance on highly known 98.7, 98.4. This suggests that maybe-known fine-tuning examples are essential for MD to correctly handle such examples during inference. It also demonstrates that with the right fine-tuning examples, MD becomes more capable of utilizing its pre-existing knowledge. Limited knowledge enhances overfitting. In 4.2, we demonstrated that unknown fine-tuning examples increase the risk of overfitting. We now observe that this also applies to weakly known, though to a lesser degree. Specifically, at convergence, D weakly known and dunk known experience significant performance drops compared to early stop, 39.2, 35.4, and 37.5, 25.8. With training to convergence, they show a modest improvement on weakly known and unknown, but substantially degrade on highly known and maybe known. This highlights that the decrease in performance is strongly attributed to an increased rate of hallucinations, facts that were already known to M after pre-training. Interestingly, DNatural performs on par with D may be known in early stop, suggesting that the mere presence of may be known examples in DSUF suffices for high performance on may be known, even if D has additional examples from other categories. Yet, DNatural's performance degrades significantly 7 after convergence, underperforming D may be known, indicating that it still suffers from overfitting, most likely due to the presence of weakly known and unknown examples. Taken together, these results demonstrate that D may be known stands out both in terms of top performance and reduced risk to overfitting. 6. Slick knowledge categories analysis. Assessing a model's knowledge remains an open problem, particularly since evaluating the quality of such methods is challenging due to the lack of ground truth about what the model truly knows. In this work, we proposed SLIC, BACA 3, a 4-category classification of facts WRT, the model's knowledge. We now further analyze and discuss our design choices, hoping that SLIC can serve as a useful taxonomy to guide future research on this subject. Fine-grained known categories. We first reflect on whether our choice of splitting known into more fine-grained categories based on the greedy decoding outcome has been proven meaningful. As shown in Table 2, highly known indeed captures facts with high degree of knowledge, as it can consistently exceeds 95% accuracy post-fine-tuning, while maybe known and weakly known seem to represent weaker knowledge degrees. As intended, the performance on weakly known is worse than on maybe known, but better than on unknown. Additionally, the exact categories distinction we made was proven useful, since it revealed important insights on the importance of the maybe-known fine-tuning examples, as discussed in detail in Barity 5. Benchmarking unknown test examples. A desired property for QA pairs classified as unknown that appear in the test set is that M will incorrectly answer Q post-fine-tuning, otherwise they are not truly unknown. 8. In Table 2, we can see that the accuracy on unknown is extremely low, 3.2% or less, which is a strong indicator that most of the unknown examples are actually unknown to M. Figure 5. Slick unknown categorization versus classifying examples with P true T as unknown. The x-axis is the percent of test examples classified as unknown, and the y-axis is the accuracy on these examples post-fine-tuning. The yellow line is P true for T in. Our unknown category is the blue circle, and the blue line corresponds to approximating P correct with less than 10 random four-shot exemplars, see Bakshak 3 and Berger C. As a case study for comparison, we analyzed the P true approach by Kadavath et al. 2022, a continuous score that estimates the probability a model assigns to the correctness of a specific answer. P true was originally used for self-evaluating model-generated answers, while we use it to assess whether M considers the ground truth answer as correct. In Figure 5, we explore classifying examples below a P-true threshold as unknown and compare this methodology to SLIC. Our results indicate that, at least in our setting, our approach categorizes unknown examples for which the model's performance after fine-tuning is significantly worse. Specifically, looking at fixed values on the x-axis shows that if we would label a similar fraction of test examples as unknown using both methods, the accuracy on the P-true-based unknown examples would be much higher post-fine-tuning. Lastly, the blue line shows that using samples from multiple few-shot prompts to approximate P-correct is crucial, as using next 10 leads to higher test accuracy on SLIC. Unknown examples. 7. Discussion. Practical implications. This work highlights the risk in using supervised fine-tuning to update LLM's knowledge, as we present empirical evidence that acquiring new knowledge through fine-tuning is correlated with hallucinations, WR, to pre-existing knowledge. Additionally, this work raises important questions for future exploration regarding in fine-tuning practices. We saw that unknown examples are fitted slower than the known ones, thus their negative effect manifests as a form of overfitting, which emphasizes the importance of using early stopping instead of a fixed number of fine-tuning steps. However, early stopping may be less effective when fine-tuning on numerous tasks with distinct optimal stopping points. An alternative solution can be to align the fine-tuning data with the model's knowledge by filtering out unknown examples. We show initial evidence that this can reduce the risk of overfitting without compromising performance. A possible drawback of filtering is that unknown fine-tuning examples can still be useful to teach LLMs to express uncertainty on unknown test examples. This raises the question, can relabeling unknown fine-tuning examples with uncertainty expressions, e.g., I don't know, reduce their negative effect? Our preliminary experiment, described in Fashik K, suggests that the answer is yes, which indicates that such approaches could be the most promising. Exploring this is an interesting direction for future work. Superficial alignment hypothesis. Zhou et al. Hypothesized that the knowledge and capabilities of LLMs are mostly learned during pre-training, while alignment is a simple process where the model learns the style or format for interacting with users. They substantiate this hypothesis by showing that fine-tuning on just 1K high-quality examples can result with a competitive assistant LLM named Lima. As discussed in 4.3, we show evidence that LLMs struggle to acquire new knowledge present in the unknown examples and mostly learn to utilize their pre-existing knowledge. We also showed that fine-tuning on highly known examples led to suboptimal utilization of pre-existing knowledge, despite our task format being simpler than Lima's and our dataset being 6 times larger. Taken together, our findings suggest that even though most of the LLM's knowledge is indeed acquired through pre-training, the model learns more than just style or format through fine-tuning, as the selection of fine-tuning examples significantly influences the model's capability to utilize its pre-existing knowledge post-fine-tuning. 8. Related work. New knowledge and hallucinations. Schulman, Goldberg, and Gudeband et al. Mention the conjecture that fine-tuning on new factual knowledge may encourage hallucinations. Huang et al. Categorized hallucination causes and formally defined this scenario as capability misalignment. They highlight that limited research addresses capability misalignment due to the challenge of defining the knowledge boundary of LLMs. Kang et al. Showed that when a fine-tuned LLM encounters unknown queries at test time, its responses mimic the responses associated with the unknown examples in the fine-tuning data. Yin et al. Showed that LLMs' performance is not satisfactory when they face new knowledge in their input contexts. And Li et al. Analyzed the impact of unknown in-context learning examples. To the best of our knowledge, our work is the first to empirically assess the impact of exposure to new knowledge through fine-tuning on tendency of the fine-tuned model to hallucinate. Quantifying knowledge in LLMs. SLIC can be seen as a confidence elicitation method for the ground truth label, M knows Q, A if it is confident that A is the answer to Q. Existing work derive calibrated confidence from LLMs by examining agreement across multiple samples, probing internal representations, eliciting verbalized probability, Tian et al., 2023b, or direct prompting. Kadavath et al. Also trained a separate PIK model to predict if the LLM knows the answer to Q. The label for PIK was approximated by the fraction of correct sampled answers, which is conceptually aligned with pcorrect 3. A key difference is that we also define the SLIC categories and provide evidence that we capture meaningful and useful categories. 9. Conclusion. We study the impact of integrating new factual knowledge through fine-tuning on the model's tendency to hallucinate. We first propose SLIC, a categorization of facts.rt LLM's knowledge. We then design a controlled study where we isolate the impact of new knowledge and rigorously evaluate its effects. We provide multiple insights on the fine-tuning dynamics with the following key findings. 1. Acquiring new knowledge via supervised fine-tuning is correlated with hallucinations to pre-existing knowledge. 2. LLMs struggle to integrate new knowledge through fine-tuning and mostly learn to use their pre-existing knowledge. 10. Limitations. Our experiments were conducted using a single LLM, and thus it is unclear whether results will vary with different LLMs. Having said that, our study is extremely compute-heavy and thus challenging to replicate on multiple LLMs. First, our fine-tuning is compute-heavy as its runs are very long, as we wanted to analyze the behavior during different stages of fine-tuning, including the overfitting stages. Second, and most importantly, to facilitate our study, we needed to annotate a large-scale dataset under the SLIC categories. To derive reliable conclusions, it was crucial to accurately assess the model's knowledge under a single fine-tuning example. In our case, we run 170 inference steps per example, i.e. more than 15 MIMIM inference steps to categorize our full dataset. In addition, since we focus on closed-book QA, the practical implications from our study, such as filtering out unknown fine-tuning examples, still require validation in settings involving long-form text generation. To filter out examples that introduce new factual knowledge in long-form generation tasks, one would need to make adaptations to SLIC and come up with an effective way to compare the sampled answer with the ground truth to approximate p-correct. We leave this for future work. Long-form generation tasks introduce evaluation challenges, leading to a wide adoption of LLM-based evaluations. Our choice to focus explicitly on closed-book QA facilitates more accurate evaluation that enhances the reliability of our findings. Lastly, we did not test the effect of adding additional fine-tuning examples from diverse tasks into the fine-tuning mixture. While this could more closely approximate a typical instruction fine-tuning scenario, such dataset extension may introduce new factual knowledge in an uncontrollable way, which will limit our findings. 11. Acknowledgements. We would like to thank Ori Ram, Uri Shaham, Alon Jacovi, Mor Ventura, Yochai Blau, Eyal Ben David, Avi Kachularu, Avi Natan Hasidim, and the members of Roy Reichart's NLP group for reviewing the paper draft and providing valuable feedback. Special thanks to Yuri Shaham for assisting in setting up the fine-tuning pipeline during the early stages of our research. B. Test performance as proxy for hallucinations. We now detail the relation between the test performance in our setting and hallucinations. In our study, poorer performance of a fine-tuned model MD1 compared to another fine-tuned model MD2 on the test set can be attributed to a higher rate of hallucinations in MD1 relative to its pre-existing knowledge, due to the following explanation. The test set can be conceptually divided into two types of questions. First, there are questions with answers that are unknown to M. Those questions will remain unknown post-fine-tuning as we make sure that the training set is disjoint from the test. Table 3, statistics of the NT questions train split annotated with slick categories. We annotate the entire train split but always fine-tune on exactly 6,142 examples. See the min column E for more details. Table 4, in-distribution test set statistics set back A. This means that both MD1 and MD2 will fail to answer these questions. Thus, the test performance difference between MD1 and MD2 is mostly attributed to the second type of questions, ones that are known to M, i.e. M can answer them correctly since it possesses the relevant knowledge. Thus, MD1 and MD2 must rely on their pre-existing knowledge to answer such questions, and a lower performance on such question can be only categorized as an hallucination WR to pre-existing knowledge. See P-correct approximation. This section expands back 3 with additional details about our P-correct approximation. In our study, we approximate P-correct QA-MT based on the fraction of correct answers to Q sampled from M. We begin with randomly sampling next distinct K-shot exemplars for each relation in our dataset, Proc A. Then, to approximate P-correct QA-MT, we use M to generate answers to Q using each of the next exemplars from the relation corresponding to Q. We first use temperature sampling with T equals 0.5 to sample N-sample answers for each of the next exemplars. P-correct QA-MT of 0 is then approximated by the fraction of correct answers from the total of next N-sample predictions. We also generate the greedy decoding prediction T equals 0 for each of the next exemplars. P-correct QA-MT equals 0 is then approximated by the fraction of correct answers from the total of next predictions, point 13. We use K equals 4 in our study, simply since we found it enough for M to output answers in the correct format. We use next equals 10 and N-sample equals 16. The N-sample 16 samples using T equals 0.5 are sampled from top 40. The K exemplars are sampled from the development split. We sample next different samples since we found that even when the few-shot exemplars are sampled per relation, their exact choice still affects the prediction. In Berkeke 6 and Figure 5, we show Table 5, out-of-distribution test set statistics. Table 6, error analysis of 100 predictions of the pre-trained model for which exact match is false. Evidence that this also improves the quality of our categories. Below is an example of our 4-shot prompt format from real example from entity questions with the relation P106 representing occupation, point 14. The question in this case is, what kind of work does Ron Konopka do? And the ground truth ASNOR is, geneticist. What kind of work does Nicholas Roeg do? Film director. What kind of work does Crystal Giuffre do? Actor. What kind of work does Maurice Blondel do? A philosopher. What kind of work does Xavier de Burgos do? A politician. Q. What kind of work does Ron Konopka do? To decide whether a sampled answer is correct, we use the exact match, EM metric, to compare it with the ground truth answer. The main advantage in this choice is that when EM is true, we know that the answer is correct for 100%. The main potential risk associated with this choice is that we may wrongly classify answers as incorrect due to paraphrases or answers with different granularity levels. To address this, we perform an error analysis on 100 predictions for which EM was false. We randomly sample 50 greedy predictions, T equals 0, and 50 samples with T equals 0.5. The results are in Table 6. This analysis suggests that in 90% of the cases where EM is false, the predicted answer is indeed incorrect, which is a reasonable performance for our purpose, especially considering that when EM is true, the answer is 100% correct. D data annotation, we first calculate P-correct QA-MT equals 0 and P-correct QA-MT 0 for each QA pair in our preprocessed dataset, 2 and PK A, using our P-correct approximation, 3 and beta C. We then use these values to categorize each QA pair into one of our 4 categories, Pack 3 and Figure 2. We provide the full statistics of the categories on the train and test set, as well as the out-of-distribution test set in Tables 3, 4, and 5. Fine-tuning details fine-tuning data. In FAGIC 4, we examine the effect of new knowledge in the fine-tuning dataset D on the performance of MD by varying the proportion of unknown examples in D. When we create variants of D with exactly X% of unknown and 100 minus X% known examples, we make sure that the relation distribution remains consistent. To achieve that, we sample X% of unknown from each relation. In 5, we create single category variants of D. Since we want to work with a fixed D across all variants, we want to make sure that we have D examples from each category. To ensure this, we measure the size of the smallest category in each relation, see the min column in Table 3, and define D as their sum. In other words, for each relation we calculate the size of the smallest category and sum these values. This leads to D equals 6:142, as illustrated by the last column in Table 3. More formally, for each relation R in the training split and for each category cat from our 4 slick categories, we define cat R to be the examples from category cat in relation R. Consequently, size cat R is the number of the examples in cat R. For example, size highly known P131 equals 553. See Table 3. We then define, see equation, where our train are the 12 relations from the training set. Below is an example of our data format in the train, development, and test sets, from real example from entity questions with the relation P106 representing occupation 15. The question in this case is, what kind of work does Ron Konopka do? And the ground truth Asnor is geneticist. Answer the following question. What kind of work does Ron Konopka do? Fine-tuning hype parameters. We fine-tune every model for 50 epochs for all our model variants to completely fit the training set, so we can examine all stages of fine-tuning. We use learning rate of 1E5, a batch size of 128, and a dropout rate of 0.05. We evaluate the models every epoch on the development set. The early stopping criteria is defined to be the epoch with the maximum accuracy on the development set. Train accuracy on different known categories. In FADIC 4.3, we analyze the fine-tuning dynamic and present the training accuracy as function of the fine-tuning duration in Figure 1. For simplicity, we treated the known categories collectively. For reference, we also include the plot with the full per-category breakdown in Figure 6. G-linear model. In FADIC 4.4 and 4.5, we use a linear model, equation 1, that predicts that test accuracy and the out-of-distribution test accuracy. We estimate the parameters of this linear model based on results from all our variants of D used in FADIC 4. For all these variants, we measure the test accuracy and the number of known and unknown fine-tuning examples that M fits during different fine-tuning stages. This way, we collect a dataset with examples of the form accuracy NKN, which we use to fit a linear regression model. Figure 6. Training accuracy as a function of fine-tuning duration, evaluated on the variant with 50% unknown fine-tuning examples. For reference, we also include the accuracy on the development set, accompanied by a zoom-in plot within a narrower range to provide a more visible and clear view. Out-of-distribution, OOD, evaluation. In BAE 4.5, we discuss out-of-distribution OOD results. In these experiments, we simply used our OOD test set consisting of 7 relations unseen during fine-tuning, CA. When we performed the analysis discussed in 4.1 and BAE 4.2, we additionally evaluated the models on the OOD test set. For completeness, we add here Figure 7, which is the out-of-distribution version of Figure 3. Figure 7a presents the OOD test performance as a function of % of unknown examples in D for different fine-tuning duration. The corresponding in-distribution results, Figure 3a, were discussed in 4.1. Figure 7b presents the OOD test performance for the ablation where we filter out unknown fine-tuning examples. The corresponding in-distribution results, Figure 3, were discussed in 4.2. We notice that similar trends, just with a smaller overall magnitude of the performance drop, up to 6 points drop compared to up to 14 for in-distribution. This smaller drop magnitude is also reflected in smaller values of N, Table 1. Figure 7, performance on the out-of-distribution OOD test set as a function of the percent of unknown examples in the fine-tuning dataset D. This plot is the OOD version of Figure 3. Everything is similar to Figure 3, except that y-axis is the accuracy on the OOD test set. We note that the development set did not change, not OOD, thus it does not necessarily reflect the optimal stopping point for OOD. Table 7, a copy of Table 2 with detailed notation of the statistically significant test results. In each column, statistically significant differences from the best result are indicated using Heisch and for p.05 and p.01 respectively. Statistic significance tests. In Exercise 5, we present Table 2. As mentioned in the caption, we perform statistic significance tests for each column. To this end, we compare all the values to the maximal value in this column. For each subset of the test set, we randomly shuffle all the examples in it, split them up into 100 approximately equally sized subsets, and compute accuracy for each of them for all the models of interest. We then apply paired sample t-test with p.01. In Table 2, the best result is in bold, as well as all the results with statistically non-significant difference from the best with p.05. We additionally include a copy of Table 2 where all the statistical tests' outcomes are annotated. See Table 7. We can see that in almost all cases the difference is statistically significant with p.0.01, except 2 cases where it is only with p.05, d natural unc and d may be known n. Since we also discuss horizontal comparisons, where we compare early stop to convergence, we additionally run significance tests, not annotated in Table 2, for all, comparing early stop to convergence. The difference for d may be known was not statistically significant, while for all others, including d natural, it was significant with p.0.01. The true case study. In Book 6, we used the p-true metric from Kadavath et al. 2022 as a case study for comparison. In Figure 5, we compare our unknown category versus classifying as unknown based on a threshold of p-true. We calculated p-true for every QA pair in the test set using Kadavath et al. 2022's prompt. Question: where is Paris located? Proposed answer: France. Is the proposed answer A, true, B, false? The proposed answer is: we then treated QA pairs with p-true below a threshold as unknown. We experimented with each. Table 8, results of our initial experiment where the label of the unknown fine-tuning examples is replaced with I don't know. D in this case is the variant with 50% known and 50% unknown. DIDK is the variant where all the 50% unknown fine-tuning examples were relabeled with I don't know. The accuracy is measured on the subset of the test questions that were answered, i.e. MD did not respond with I don't know. Possible threshold T in according to our test set. For each threshold T, we then measured 1. How many examples were classified as unknown out of the test set? 2. What was the accuracy on these examples after fine-tuning? We plot the results in Figure 5, where p-true is represented with the yellow line and our unknown is represented with the blue circle. As discussed in Figure C, it was approximated using 10 different samples of 4-shot exemplars, NEX equals 10. We also check smaller values of NEX and plot the results with the blue line. The accuracy after fine-tuning for all the results is measured after fine-tuning with D natural, Fascia 5. K relabeling, unknown, fine-tuning example with an uncertainty expression, initial experiment. In this work, we showed that fitting unknown fine-tuning examples negatively affects the test performance. However, this negative effect manifests as a form of overfitting. From practical perspective, we showed that we can mitigate overfitting by either using early stopping or filtering out unknown examples from the fine-tuning dataset. We now perform a preliminary experiment where check whether fine-tuning the model to abstain from unknown examples can also be a potential mitigation. Specifically, we replace the label of the unknown fine-tuning examples with the expression, I don't know, and test whether this mitigates the observed overfitting. Table 8 presents the percent of the test questions that were answered, i.e., MD did not respond with I don't know, and the accuracy on those questions. This experiment was conducted on the D variant with 50% unknown. The first row is for the original result with D as a reference, and the second row is for the results with DIDK, where the ground truth label of the 50% of the unknown examples in D was replaced with I don't know. Consistent with the findings from previous work, we observe an improved accuracy on willingly answered test examples when comparing D versus DIDK. When we compare early stop versus convergence for D, we observe a performance drop, 40.0 per 38.8, which illustrates the overfitting effect. However, we observe that relabeling the unknown examples with uncertainty expressions seem to reduce the risk of overfitting. Specifically, the accuracy for DIDK remains 61.8 for both early stop and convergence, with a small decrease on the number of willingly answered questions. This concludes the reading of Does Fine-Tuning LLMs on New Knowledge Encourage Hallucinations? On Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.